Hello, my name is Elif Aygün, and this is my cavity resonator design project for Applied Electromagnetics EEE 352 course. First of all, I want to start with giving a brief explanation for cavity resonators. In low frequencies, typical R, L, and C components may be used without any problems to build resonators. But in high frequencies, such as our bandwidth, which was between 500 MHz and 1.5 GHz, these components becomes inefficient because, first of all, they interfere with each other, and secondly, because of signal effect and energy loss in high frequencies, we observe high effective resistances. To solve this problem in microwave frequencies, of course, we use closed forms such as rectangular cavities. A cavity resonator has a conductor material for each enclosure, and basically it contains EM waves that reflect inside. In my experiment, I designed a cavity resonator for 971 MHz. For my resonator, I choose TE101 mode. This is the resonant frequency formula, as you see on the screen, which is applicable for each mode. Note that for TE101 mode, only A and D affect resonant frequencies. Therefore, we are going to only use A and D components of this frequency formula. In order to be able to do that, I set M and P as 1 and N as 0, and I take U as C, which is the speed of light. Then I calculate A and D such as 30 and 18 centimeters. To be able to calculate B, first I calculated the wavelength, which is 30.89 cm. Then, since the antenna length should be lambda over 4, in other words, it should be equal to wavelength over 4, we will take the antenna's length equal to 7.5 cm. Finally, since the B component should be larger than antenna's length, it can be taken as 11 cm. In the experiment, I placed the probe that I use for excitation in the middle. Then, in return, when I excite the probe, this is what I obtained. For my resonant frequency, I obtained 906 MHz with 20 dB return loss. And the other two frequencies are the other resonant frequencies since my cavity is not in a cubic form. And the other frequencies are 1.3 GHz and 1.2 GHz. For the second part, I placed another probe in the middle, and I just placed the first probe in the 1/4 length. Then I did my measurements for obtain input and output signals. For 906 MHz, I obtained 1.47 dB of power loss, and for 1.2 GHz I obtained 7.8 dB, and for 1.3 GHz I obtained 6.9 dB. These are calculated using the power loss formula, which is 10 logarithm of output voltage over input voltage. This is what I obtained for 1.2 GHz. This is what I obtained for 906 MHz, and this is what I obtained for 1.3 GHz. As we can see, as the frequency gets away from 906 MHz, which was this, the output voltage value decreases, and the most high output value that we can obtain is seen in 906 MHz, which is the calculated resonant frequency. Note that here the obtained and measured resonant frequency is different than the calculated one because of the fact that I used aluminum foil to cover the inside of the box. And when we cover a box with aluminum foil, decreases occurs, which decrease the reflection happening in the box, which affects the resonant frequency. Thank you for listening.